All right, today we are diving deep into one of the most powerful technologies shaping our world, neural networks. And don't worry about the crazy jargon. We're basically going to build a digital brain from the ground up and see exactly how it thinks.
Everything really kicks off with this one simple but super powerful question. For decades, this was just the stuff of science fiction, right? But the concepts we're about to explore are making it a reality. And look, this isn't just about making computers calculate faster. We're talking about creating a machine that can actually learn, recognize things, and make decisions on its own.
Okay, so let's get right into it. If we want to understand how an artificial mind works, we've got to start with the original blueprint, right? The human brain. Okay, so this is the core idea right here. On one side, you've got the biological neuron, the tiny cell that's the building block of our own brains. And on the other side, you've got its digital twin, an artificial node. An artificial neural network, or ANN, is really just a huge collection of these nodes, all connected and working together to try and copy how our brains get things done. So you might be wondering, how are all these digital neurons actually set up? Well, it's actually a pretty elegant and simple structure. Data, any kind of data, comes in through what we call the input layer. Then it gets crunched and processed in the middle in one or more hidden layers. And finally, a clean answer pops out of the output layer. The information just flows forward from one layer to the next. All right, so that's the 30,000-foot view. But what's really going on inside? How does just one of these little nodes actually think? To really get it, let's zoom all the way in and watch one make a simple, real-world decision. Let's imagine our little artificial neuron is having a beach day, and it has a really, really important choice to make: to surf or not to surf. That is the question. So to make its big decision, our node looks at three key things. First up, are the waves any good? Yep, so that gets a 1. What about the crowds? Is it packed? Nope. Beautiful empty day, so that's a 0. And kind of important, is it shark-free? Thankfully, yes, so that gets another 1. But, not all of these factors are created equal, which brings us to that importance or weight column. And that right there brings us to this absolutely critical idea of weights. This is basically how the node decides what's important. Having great waves is like the most important thing, so we give that a really high weight, a 5. No sharks? Yeah, that's also super important, so it gets a 4. The crowds? It's a factor, but not a deal breaker, so it only gets a weight of 2. Okay, so here's where the magic happens. The node does some really simple math. It takes each input's value, the 1 or 0, multiplies it by its weight, adds all those up, and then subtracts a number we call the threshold. And that threshold, just think of it like a minimum score. You got to beat this number for the node to get excited and say yes.
So after you run the numbers, you get 6. Just a single number, but it holds the key to our whole decision.
And because 6 is a positive number, it's bigger than 0, it totally cleared our threshold, the node's output is a 1. And what does 1 mean? It means yes. The decision is made. We are going surfing. See? Pretty simple, right? Now just imagine millions of those decisions happening all at once. Okay, but this is where things get really, really cool. A neural network isn't just a one-and-done calculator. If it makes a bad decision, it can actually learn from its mistake. It's designed to get smarter all by itself. You see, this learning process is what makes these networks so unbelievably powerful. Unlike regular old programming where a human has to write every single rule, a network teaches itself. First, we give it a ton of data where we already know the right answer. We call that supervised learning. Then we check its work. How wrong was its guess? We use something called a cost function for that. Based on that error, it goes back and just slightly tweaks all its weights to do a little better next time. That's a process called gradient descent. And finally, we just repeat. We do that cycle over and over and over and over again, millions of times, until the network becomes crazy accurate. Let's zoom in on that cost function for a second. The easiest way to think about it is like a score in a video game, but for how wrong you are. If the network gets a perfect answer, its score, the cost, is 0. Awesome. If it's way, way off, the cost is super high. So the entire goal of training is just to play the game over and over, tweaking all those weights to get that cost number as low as digitally possible. All right, so we've got this basic building block that can make a choice and even learn from its mistakes. But, just like our brains have different parts for seeing and hearing, there are specialized neural networks built for very specific jobs. And two of the big ones you'll hear about are CNNs and RNNs.
Convolutional neural networks, or CNNs, think of them as the artists or the detectives of the network world. They're amazing at spotting patterns in visual stuff, which is why they're perfect for things like facial recognition on your phone. Recurrent neural networks, on the other hand, they have a kind of memory. They have this neat little feedback loop inside. This makes them absolute champs at understanding things that happen in a sequence, like, say, human language, or even trying to predict where sales are headed.
And all of this brings us to one last really big question. We've built these incredible systems that can recognize faces, predict trends, and make decisions with shocking accuracy. But are they just incredibly sophisticated calculators, just matching patterns with math? Or is there something more happening inside these digital minds? That's the question that's really going to define the entire next chapter of artificial